Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about energy conversion for increasing efficiency. So it sounds counterintuitive, but let's dive deep into it. So first thing we have to understand, efficiency. And yes, we are not breaking second law of thermodynamics. So relax, take a chill pill. Do not worry about it. We are not breaking the law of thermodynamics. So if you think that conversion must waste energy, that is absolutely fundamentally true. However, you have to understand some real things here is that efficiency, what the heck that means? That simply means useful output of power per unit of fuel input. Meaning if you are putting X amount of basically fuel, you should get Y amount of work, useful work, not waste heat, useful work. So if that's because this is the biggest if this energy conversion does not work in most scenarios, but it does work in some scenarios. So condition applied is if real world is causing higher waste heat, meaning this system basically you have fuel and your waste heat, there would be a percentage. Let's say the percentage in ideal scenario, the manufacturer said like, hey, the efficiency would be 35%, and you are saying, hey, best case I'm getting 20%. In that scenario, conversion would allow you to gain back some things. Now, is that happening in real world? Well, to give you a context, this is data from Statistician, is that back in the days of 2001, if fuel companies were selling you a car, basically car companies, and they were like, hey, our mileage is this much. So mileage that they were stating versus mileage you were getting, they were off by 9%. By 2016, it had become 42%. Given the fact that now, I have experience of driving a car and actually measuring mileage, and given the fact that it's a fixed route, known thing, everything is known, I have noticed that my car on day one from the lot, it was like awesome. Now it's like, dude, like company was claiming bonkers amount, like 35 or something. We were barely getting like 22. I was happy. Any number above 20, me good. I'm getting 18 now. Like my car itself, and again, it has not been driven. It rarely is driven. So the kilometer, and I've been gone through servicing. Turns out it's the experience of everyone. So something happens where in principle you're supposed to get a lot of mileage, but in real world you get this. You just get smoke. You're not getting actual work. All you are getting is waste heat. If you have that scenario, only then conversion can help you. So let's understand this with example. That will make it far more clear. So let's take an example of locomotive. This has been indirect drive for so long that it's like we think of locomotive, we think of indirect drive or diesel electric drive. So what we used to have back in the days of 1950s is that we had prime mover, okay, your engine, the main puppy, and that used to drive transmission with fluid coupling or whatever have you. Transmission used to drive the wheel, done. Now here's the deal. We built this, we tested them, and outcome was poor mileage. That did not make any sense. Then right now, what we do right now is that we have a prime mover. That puppy moves a generator. That generator sends the energy, goes into converter, which again, it takes the AC, makes it into DC, and then again makes the DC into AC. That puppy goes to the motor, and now we get more mileage. It's like that should not be possible. Like you went from mechanical, basically fuel to mechanical energy, okay, right? You did fuel, boom, you got mechanical energy went into transmission, which is mechanical only, mechanical, wheel is mechanical. So from that scenario to mechanical to electrical to different type of electrical to again electrical to mechanical again. How the heck that's happening? Like it should not make sense. It should not be possible. But here's the interesting part. You have to study the reality of ICE engines. It does not matter which fuel you are talking about. It does not matter it's running on kerosene, does not matter running on diesel, does not matter running on petrol. If it's a ICE engine, internal combustion engine, it will have a very narrow spot of torque and RPM. Both have to be locked. Only then it can give you maximum energy extraction. Extraction from where? Fuel. Fuel have a fixed amount. But your engine's ability to extract that, it's very dependent on torque and RPM. So once we realized that part, so detaching this allowed us to keep the engine in its sweet spot. The bigger the like sweet spot of engines are very narrow, like this is the how it's given. Basically one axis would be torque, another axis would be RPM, and the vertical axis would be your efficiency. So you can see there is like a tiny spot, like a peak. This is where you want your engine to be. But realistically, if you have direct drive, meaning you take a prime mover and transmission, it will always be somewhere here. Because again, even you be like, hey, what if I'm starting the train? Okay, your torque requirement would be maximum. Heck, if it's a heavy train, you will be loading the RPM. So you are in worst place. Then okay, let's say it started to move up. Now you will change gear. Okay, RPM start to come down, but torque will keep remaining until your train reaches a full point where it's like full speed or track speed is there. Then you slowly edge back on the torque. So you can notice that, like, even though engine on test stand in real world condition would be like this temperature, this humidity, would be like we should get let's say efficiency of 35%. Realistic, you will be lucky, you will be having party if you can achieve 15% efficiency. That's why detaching from transmission allowed us to have such higher efficiency. Now, like, how the heck this puppy detaches it? Here's the deal. So imagine you are running a train. Train has what we call notches. Each notch is directly corresponded to specific RPM and a specific torque. Now, like, okay, RPM we can understand. Engine RPM is very easy to control. How the heck you are controlling torque? Well, we directly are not. What we are controlling is the current that is going into the rotor of the generator. So that is how we are controlling the torque. To some extent, it's not completely isolated, but to some extent we can control where the torque is. So what happens? Let's say your train, a locomotive, is pulling a train. Lot of passenger boards in. Your train is very heavy. You put it in a notch and you start the engine. Okay, what happens? The electronics does its thing. You set it in a notch, electronic does its thing, RPM reaches the optimum point, torque, it tries to reach optimum, but here's the deal. Your electric motor will only drive as fast as they can drive, meaning if they are very heavily loaded, instead of accelerating in 3 minutes, it will accelerate in 4 minutes. Instead of reaching, like, let's say in flat line, instead of reaching let's say 100 kmph, it will only reach 90 kmph if it's too loaded. And opposite will also work. Let's say it goes to a station, lot of people debark and the train is mostly empty. Again, driver will still set the same notch, but now the top speed will slowly edge up, where it's like, oh, in the same notch, instead of driving at, let's say, 100 kmph, now it will be like 102 kmph. It will reach a equilibrium, trying to keep the engine in sweet spot. Now it tries to keep it. It's not absolutely there, but it is fundamentally better than transmission. And engineers calculated it, like how many gears it will take to keep that sort of efficiency. Is like, yeah, the number of gear required, it will be 2 bonkers, almost like CVT. But given the fact that CVT cannot handle that much torque, it did not make any sense. So that is why we have this. Basically, we are trying our darn best to keep our engine in sweet spot, sweet torque and sweet RPM, where it gives the maximum love. So, because again, fuel is expensive and you are consuming boatload of it. So this approach is the best way we have been driving our trains for last 50 years. Like heck, back in the days, we used to have a DC generator, dynamo they were called. Then the dynamo were heated, and then we put basically bridge rectifier. Bridge rectifier removed the brushes, so it became more efficient. And again, diodes wasted energy, but again, it saved energy on the brushes side. So it's always something like that. You always have to understand, are you in the sweet spot? Are you wasting somewhere else? And again, in case of bridge rectifier, it was done primarily to save fire hazard. Generators used to catch fire. Brushes that were here, it was handling megawatts of power. They were catching fire. So that's why we locomotive with basically prime mover, generator, controller, and then motor gives you more mileage, because it allows the generator its best. It's not completely buffered, but it's very best where it tries to stay in the peak of efficiency. Then we come to the new component. There is a very good chance you may have bought this or may have heard about this, is inverter generator. It's a kind of a sweet spot technology where it works for small scale generator, not for big puppies like this, but puppies like this, where it's like, 1 kilowatt or 2 kilowatt, generally under 5 kilowatt. Again, it can be made for this puppy, and yes, it will be efficient. It's just cost does not make sense. Here, it does make a lot of sense. So gens have to have locked RPM. That's the biggest hassle with generator designs. Now you will be like, why? Well, most of the time, generator's rotor is running something known as synchronous generator, meaning whatever topology. Synchronous generator simply means the RPM is directly proportional to the frequency. If you are in India, it would be 50 hertz. If you are in USA, it would be 60 hertz. RPM will be directly locked to that. For example, in case of a generator, it could be 1500 for 50 hertz, and it could be 1860 if I'm not mistaken for 60 hertz. RPM would be locked. You can calculate that, like the type frequency to poles of the motor to get the RPM, same thing. So that forces RPM to stay locked. For example, let's say you have a generator and you are like, okay, power is out and I have to run the air condition. Okay, when does air condition takes a lot of energy? Starting time, right? It's like starting out, trying to bring the temperature and pumping a lot of heat, consumes a lot of energy. Now, here's the interesting part. At that position where you are drawing a lot of power, let's say this is 3 kilowatt and let's say this is 3 kilowatt, and you are draining 3 kilowatt out of both of them, this will be a bit more efficient and this will be more or less the same. But here's the deal. The moment that load goes off, meaning you are driving the AC is like, okay, I finally cooled down, let's shut off the compressor. It's like, oh, this will get stuck. It's like, I still have to maintain the RPM because again, I'm frequency locked. This puppy will be like, oh, load is low. How about we reduce the RPM? Now, how can it reduce the RPM? Well, it's not directly coupled. It has conversion. It takes the generator makes basically drives a BLDC. And yes, all motors are generator. So it drives the BLDC, that BLDC drives the inverter, inverter drives your load. So the moment inverter detects, hey, load is actually not drawing the power, it's like, hey, generator, prime mover in this scenario, it's like, chill bro, reduces the RPM, saves the fuel. So if you have a varying load, basically air condition like scenario, this would be wasteful, this will save you power. Like literally fuel, like you can see it, hey, in 1 gallon of fuel or 10 liters of fuel, how much how longer my generator ran will literally be different. And that's why every generator manufacturer will tell you, it's like, if you're buying a generator set, you intend to use it at 80% of its capacity. That's where it's most optimum, that's its sweet spot, because RPM is locked, 80% also locks the torque. That's where they are focusing on. If you are like, hey, only loading at 50%, yeah, you're wasting fuel, you're literally wasting fuel away. Here it's like, hey, relax, just like chill, take a chill pill, relax. So that's why even if you have generator that makes AC, AC goes to DC converter, DC converts to AC again, and then goes to your load, somehow you can still save more energy, specifically in varying load. If you do not have varying load, it does not make a difference. So if generator power plants are there are few of them in the world, like this puppy. Yeah, here it does not make a sense because these are dead loaded device, meaning I have fixed amount of RPM, fixed amount of load. I do not have to worry about anything else. They are like, shut up, take money. Here it's like, hey, I have variable load. Like sometimes my AC is like, yeah. Other times my fridge is like, yeah. Other times I'm like, I'm chill, bro. Then it's like, what the hell? Why I'm burning fuel? It's like, relax. So fuel saved in varying load. Be very mindful. Varying load. If you do not have varying load, let's say in case of India, many times we have generators to run water pumps. It won't make a difference. If I am running water pump for 2 hours, if I size the generator and motors correctly, it would be like 80% of the load. It won't make a difference. So inverter generator is also a clever way of noticing a flaw and fixing it using converters. Even though each conversion steps is wasting energy, the grand total yield is improved because you are keeping the ICE engine in a sweet spot. You're not wasting it. Basically in diesel, we are trying to keep the RPM. Here we are let RPM being free float. So this is how we solve the generator issue, small generators, inverter generator units. Then we come to Edison Truck. I've already covered this channel, but this is my personal best example that I have ever seen. It's like they have battery. It's the same concept as basically inverter generator. It's just like, what if instead of relying on capacitors to act as a short-term buffer, what if we have big ass battery? So what they do is allows this is the same graph. Basically, you have RPM, you have torque, and you have max efficiency in 3 dimensions. So max efficiency, there is a sweet spot, like where it will give the most amount of energy. Now you will like, why the heck spot is not a point? It can't be a point because ambient temperature changes, ambient humidity changes. So it does require. So the same engine controller is brought to India, it will work differently compared to Canada. So relax, it's a sweet spot, not a point. So if you have this sort of a serial hybrid drivetrain, you have the luxury of running the ICE engine in fixed RPM. Does not matter petrol, does not matter diesel. So you have fixed RPM and you have fixed torque because you can load the generator based on your requirement. You go like, hey, only load up to this percent. Like whatever the sweet spot, you will design everything so it matches and your engine stays at this system. That means, what does that mean? That simply means your fuel, basically how many liters of fuel you are consuming, you are getting the maximum amount of kilowatt hour possible. Now let's give some numbers so it makes context, because again, many times people are like, hey dude, you have so much conversion, it would be wasteful. Again, it's not. If 100 is the energy available in your fuel, okay, whatever liter, gallon, go YOLO on it. 100 was available in the fuel. So you got 30% conversion. Be mindful, many companies claim they have engines that are 35%, but that is like optimum lab condition. That is like, it has to be exactly here. So 30% efficiency, okay, you 35 they claim, 30 you can achieve, but again RPM and torque both have to be loaded correctly, so you achieve that. Now you have energy as in mechanical, you have to convert it into electrical, AC, DC conversion, DC to battery charging, battery charging to your motor drive. That means you are eating 15% of it. So 30% as in 30 units, and then you go to 85%. How much is energy is going to your wheel? So that is 25.5 units of energy is going to your wheel. Okay, not too bad, not too great, but okay. Now compare it to diesel direct drive, normal trucks. 100, it only gives you 22%. This is where your savings are coming from because of RPM changes. And that's why we have such a giant gearbox in your basically system. It's doing its best to keep your locomotive basically prime mover here, which it cannot. And not to mention jerking also helps, does not help it. So 22, assuming your transmission is 100% efficient, you're still getting only 22 to the wheels. What does this mean? This simply means even though you had so much conversion inefficiency that you added, 15% conversion inefficiency you added, you going through that electric drivetrain, you are gaining 13% of fuel saving. To make it economically viable, the target is 10%. And I mean, it's not even running as electric truck, meaning the battery could be much smaller. They have an electric truck which has its own charger. You can, again, if you are in a scenario, let's say in India, they are like, hey, the route that I'm driving does not have electric charging. So you can reduce the battery and achieve a bit more. So that's the throttle value. The target is 13% fuel savings. Aim is you must show reliably 10% fuel saving. Math checks out. Now, people might be like, okay, this 30 could go up, or like this 22 is too low. That's up to you. That's the fine tuning part of it. But this is how it's done. This is the sole reason why we do inverter generators. This is the sole reason we do a diesel electric locomotive. It's like on paper, your engine should be like, awesome, bro. Heck, look into videos of car engine manufacturers. How much hassle they go through just to make sure it's efficient at high RPMs, it's efficient at low RPMs. Like the engineering, the cam design, the variable vibram flapping. I'm like, dude, throw all of that away. Have an engine, just run at 1 RPM and 1 torque loading. The mileage they will give, the amount of kilowatt hour extracted would be like, whoa. And yes, could we have done this before? No. Back in the days, the only way we had the ability to do it is direct drive. Heck, inverter technology became good enough to drive locomotives as in late 1970s. And by 1980s, people were actually testing it. By 1990s, it became a thing. And the high frequency system, high efficiency system that we have today is a very recent thing, after 2010 kind of recent. So this 85% efficiency was not easily achievable. Now it's just Control C, Control V, meaning you can pick up a phone, call manufacturers, and they can sell you the things. So, and all this 22, all this without regen. I did not even consider regeneration braking. This is direct drive, just on a random road condition. So, what are other benefits? Other benefits include smaller internal combustion engine. Like, does that mean all the internal combustion engine on normal trucks are overbuilt? Absolutely. Then why they are overbuilt? They are overbuilt for pickup, not for driving. Driving does not consume that much energy, but pick up when you are fully loaded as much as 60 tons. That takes oomph. That takes serious amount of oomph to load it. That fundamentally means you are wasting energy most of the time. And again, fuel mileage speaks of it. So this company did a very clever thing where they are like, hey, we have a very smaller engine and we have 2 drive motors. And again, you can see the same design philosophy in a Tesla truck where they have if I'm not mistaken, 3 basically motor units, and one of them is completely disconnected. Only when you press the accelerator, as in like you are trying to merge into a highway or where you need that oomph, that real oomph. At that point, it's like it uses an extra power unit. Most of the time, it will be disconnected from clutch. That's how much energy is needed. So what they have is like 2 drive motors, as in 2 powered axles, and each of the axle itself is 300 horsepower. Now the generator is only 335 kilowatt, basically 400 horsepower around that zone. It's like, wait a minute. So it's underpowered? Yeah. Does that matter? No. Why not? Well, this maximum oomph only would be needed when you are accelerating at full load, which again, you will do that, but only for a short duration. After the moment you reach your speed, you're like, okay, chill off. Your energy requirement will go down. So at that point, this generator is like, will be in surplus mode. And again, because generator is in this zone spot, as much as it can be, the energy that you are putting into your batteries would be much higher. And the battery chemistry is specifically chosen for that reason. The battery chemistry is lithium iron, not lithium ion or lithium polymer. Lithium polymer has the highest energy density, but also has the highest boom potential. So does lithium ion. Lithium iron does not have same oomph, but it does have the oomph in terms of discharge, meaning it can survive 4C, meaning take its capacity, multiply it by 4. That's how much energy you can drain out of it, and cells would be like, me good, me do not care. So that's why they can have such a small generator, because again, the peak loading, whenever the truck driver will be like, bam, go, the battery will be like, whoa, 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 you're draining so much energy. And 2 axles are like, I got this. And regen works in reverse. Plus they have redundancy driving, meaning same way Indian electric locomotive, what they have is a giant 25 kV pantograph. 25 kV goes into a transformer, a huge transformer. Generally, they are underslung, and that transformer has 2 separate coils. They're like, why? Well, it's designed in such a way that each bogie has its own unit, meaning if electrical failure, which does happen, rarely, but does happen, if it goes boom, which does happen, it will not, basically have a whole train stuck. All it will do is like, okay, half power now. So instead of 6,000 horsepower, you will go back to 3,000 horsepower. If a train was in motion and then this happened, not that big of an issue. If train is resting, starting time, again, train will accelerate much slowly. Train will be, top speed will be much lower, but it will still work. And benefit of that is like train can go to depot before like, I'm completely stuck. So people may not even notice, like we will only notice because it will be staying in the station for a bit longer. So if normal station break would be, let's say 5 minutes, it would be there for 10 minutes because they're swapping the engines. So that's why redundant drive. It has 3 layers of driving, meaning first you have 2 things that are actually driving. That's awesome. And does that mean like internal combustion engines are not reliable? Well, they are reliable, but what if they are not? Like in India, it's very common for them to overheat, especially if it's overloaded. What happens then? Poof, you have to wait down. Now here, that won't happen. What happens if like something breaks, which again, nothing can be built that never breaks. You can build an engine, you can build a transmission that is really good, but something bad happens, it breaks. What happens then? Stuck. Does not matter. Does not matter you have 4 axles or 18 axles. You only had 1 power source. Here, what happens if one of the axle that is electric motor driven goes lol? Okay, you still have half power left. What happens if the battery goes poof, I'm not gonna work today, whatever fault condition happens, it bypass, then the generator will drive your system. Again, it won't give you the full power, but at least it will keep you moving. So, and third case, let's say your generator unit goes offline, you still have battery power, still a low range, basically small range EV. So you have 3 modes of driving. So probability of you getting stuck with this is much lower compared to a normal direct diesel locomotive. So that's why Edison Truck is such a clever use. It's not, whoa, it's like, instead of running our engines in real world condition to 22%, what if we run the engine at 30%? So like, okay, that will require isolation. That isolation comes from battery. And again, batteries can be swappable, meaning swappable as in like, you can make it smaller. If it's a direct system where you just want efficiency, you will make battery much smaller. If you're like, hey, it's an electrical with a charger, again, then battery would be much bigger. That's up to you. You will decide it. That's the key point, keeping in this spot. Then we come to armored fighting vehicle. Now, army has a saying, it's like, hurry up and wait. Meaning you can have noticed this in Israel case also, where boom, boom happened and they're like, okay, boom, 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 everybody's going there, everybody's like armed and forces, and then they're waiting. This is a common tactic. It same happened in Russia, Ukraine. It's like day 1, boom, 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 and then everybody's like, wait. Then 5 days later, boom, 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 again, wait. 10 days, boom, boom. It happens. Like hurry up and wait. Most of the time, armies are just waiting. Trust me. So what's happening here? Well, happening is the electrical vehicle load, as in like vehicle back in the days only used to be a vehicle. That's it, done. Then some vehicle may had air conditioner, but nothing much more. Some had generators a little bit to drive the radio, but nothing major. Now it is the electrical requirement on tank system, on armored fighting vehicle systems, trucks are going exponentially higher. So why that is so? Air conditioner, like army vehicles don't have air conditioner. Well, now they are adding it because again, people have realized that global warming is actually causing temperature rise. And if your tank is sitting in air that is 45 degrees Celsius, or in case of India, 50 degrees Celsius, yeah, it's hot, meaning your soldier is, even with adrenaline shock, will not survive it for very long. It will get heat stroke. So all the new tanks that are coming, some are getting added on and other systems are like, no, we have to add it. Leopard tanks, upgraded ones, they are like, no, we have to have AC now, because again, heat stroke is becoming such a big deal. So air condition, optics, everybody loves thermal side, but thermal sides require cooling, and the higher the cooling power, the more clarity you're gonna get. If you want to see through sand dunes, and if you want to see like, okay, full dust cloud and you still want to see clearly, you have to cool it down. Like low level cooling would be Peltier cooling, high level cooling would be Stirling engine cooling, or a lot of Peltier cooling. You can have cascade Peltier cooling, so it gives you more physical robustness, and it's very inefficient, does require a serious amount of energy. You could be looking at like 50 to 60 watt to 1 kilowatt of electrical energy just to cool the sensor. If you spend that much energy, then your sensor would be very close to its optimum temperature, and then you'll be like, I can see you. I see you. So that's optics. Then we have data links. Again, radio communication has went from basic radio communication to high frequency data communication, which has a ludicrously large amount of encryption, which means idiotically high amount of computation power. So that also consumes energy. And then we have artificial intelligence. This will be added, and not to mention your gun barrel already has it. Most tanks who has like magical aiming abilities, they have it. So that also consumes a lot of electrical power, and not to mention slewing motors and all that. So electrical loads on modern design combat vehicles are going up exponentially. Back in the days, 5 kilowatt was enough. Now it's like, did we start at 50 kilowatt? So that's there. And then we come to the real world. We have fiber laser now, like this puppy. It consumes 15, basically the output, laser output they are claiming is 15 kilowatt. I had luxury of talking to people who work in laser cutting, metal cutting and all that. They are saying like you can buy 10 to 20% efficient, low cost. If you're buying some German fiber laser that could touch 35%, military are claiming they have 50%. Now, I do not know whether it's true or not, but it's theoretically possible. It's not like, whoa, it's like, okay, I can see that, now here's the deal. Think about it, 15 kilowatt, assuming magical efficiency, 50% efficiency, that means you need 30 kilowatt of electrical oomph to drive that. And this is a continuous laser, it's not pulse laser, it's continuous laser, it's a fiber laser, it's just like shh. And imagine big fighting vehicles, they are putting 300 kilowatt, continuous. Like which unit has that kind of energy? Your main engine. You cannot have auxiliary generator, which Abrams tanks have, some of them. And that's the problem. Only your main engine vehicle has that kind of oomph to drive that. Then we have railgun, which is ultimate stupidity, which I have no idea how the heck world got so addicted to railguns. This is railgun. Now you're like, wait a minute, aren't they supposed to be using electromagnet? Well, here's the problem. It does use magnetic field like this, but it does have a consequence. It welds, meaning if you have a projectile and you dump the energy, you go vabaya, energy into it, it welds rather than actually going forward. It welds itself. So that's why even in Expanse TV show, you can see that like it has spark in space. How? Well, it requires a gas charge. Now in this scenario, I cannot find the exact detail, but if I remember it correctly, it was hydrogen. They had to send pressurized hydrogen to do that, and that creates this plasma that you see in high speed. Like why there is a whoom behind it is plasma. So it will not give you stealth. These things are so bright in all spectrums that you can see it from space. Like you will know if a naval vessel fires it at you. If it's high power enough, you can see it. It's like, hey, what are you doing? So you can say that see that in Japan's version also. They have things coming out, and that's in broad daylight. It will always happen. It will be so bright in flash, you will see it. And again, that's the part that is not self-starting, and the part you need extra gas charge. There is another hassle of that. It's self-destructing, meaning it goes boom. It literally pushes itself apart. So it self-destructs. Not only it has a very brutal rusting, basically it's trying to weld itself and pushing itself. It's very brutal. That's why even though it was made as early as 2008, nobody used it. It's like, yeah, the barrel goes boom, barrel self-destructs. So what is better solution than this? Well, it does have efficiency. That's why people initially jumped into it. It does have efficiency, meaning how much megajoule is in your capacitor bank versus how much megajoule goes into your projectile. It's much more efficient. But more scary option is this puppy. This is coil gun. I do not recall where I saw this. Did I saw this in Future Weapons from Discovery Channel back when I was a kid? Because this is 2008 project. And they were making a motor firer using coil guns. Basically, the thing you that thing. So using that. Now why? Well, reality is motor is still a very powerful weapon if you can fire it without making a sound. And it just, people are there, everything is quiet. It's not like wujum, something, take cover, nothing. It's like kaboom. That's a very dangerous thing. And their target was to exceed the capacity of normal propellant charge. Now they built this. This puppy had like coils. Each coil was 25 Tesla. I'm like, wait a minute, that's too high. Isn't MRI magnets are only like 1.5 Tesla to like 5 Tesla? Well, here's the deal. First, it's a smaller unit. Second, it's pulsed, and it's far more efficient to build. Like in terms of like, can you actually build it? Yes, people can build it. Can you actually test it? Yes, people can test it. So all of this, 2008, they had it fired next to a soldier, and soldier did not well. They were showing him like live demo. It was like a carriage system where they had like accelerator and the catcher. So everything was contained, but like they fired it, and the soldier was like, what was it? Like, yeah, we fired it. Like, no sound, no sound. It does not have this issue. Of course, sound will be there if you make the projectile supersonic, because that sound barrier breakage would be there. So coil guns are very scary to me, because any smart engineer can look into it. It's like, hey, sir, DARPA, bro, don't try to remove the propellant charge. Just put RPG into it with air trigger. We're just gonna yeet it easily, because SD, action equals reaction. So if you're yeeting that puppy as hard as a normal motor, you are compressing the vehicle suspension as hard as possible. Unwise. So what if you just yeet it? Lightly yeet it at, let's say, 200 km per hour or 300 km, light yeet it, just light yeet it, and then air fire the rocket. RPGs are very cheap. So imagine a motor that fires it, and then the propellant ignites, and then range would be scary. A rocket wastes a significant amount of energy going from 0 to up. Like at up to up, it would be much higher. So that scares me. The fact that this was done in 2008, that scares me from America. And then we have to another real world aspect is like serial hybrid. If you have a serial hybrid drivetrain in your trucks and whatever have you, is that you have shore power, meaning whenever a disaster happens, armies are called to recovery and rescue efforts. The biggest need at that point is power, electrical power. If you're having, like, let's say Tesla Edison truck, all Edison has to do is buy a AC level 2 22 kilowatt charger that is bidirectional, meaning now it can pump power 22 kilowatt continuously without any issue. That's a normal thing to do. That's why, like, whenever you people hear talking about vehicle to grid, that's what they're talking about. The chargers can be made into bidirectional. It's just a very clever sequencing. It's not whoa, it's clever. So it can be done. Imagine a 22 kilowatt generator everywhere, and it's an inverter battery generator, meaning you do not have to worry about it. It's like battery would be like charged to 90%, it will start draining power from that. Load varies, no problem. Battery reaches to, let's say, you can set it for 80%. Battery reaches to last 20%, then the engine starts, fully charges it, and then shuts off. You will have very efficient, reliable power, 22 kilowatt power. Heck, it's a military system. You can put two of those unit, 22 kilowatt here, 22 kilowatt here. That will be like for bases, for rescue operation, shut up, take money. And it also allows solar power to work. So if you are in a remote area, hot area, and you can have solar power, solar panels are useless without batteries. These puppies have batteries. And again, from a military point of view, Abraham tanks, hybrid drivetrain, that's the primary reason for it. They are like, hurry up and wait. The engine will start, full charge the battery and shut off. It's like, me done, sir. Me done. Me chill. We are chilling. Like 4, 5, 6 hours, it can run all the systems, air conditioned, data links, optical systems, everything it can run without doing that. And if it detects the enemy and it chases after it, engines will literally start up, and before that, battery will be taken care of it. Battery will be like, bro, I got this. Especially if it's a lithium titanate battery. Those puppies are super capacitors. So we are reaching a world where we need power rather than gunpowder. So we need serious amount of it. Any country that is not pouring effort into hybrid serial drivetrains, yeah, they're gonna be stuck, like very seriously stuck. And that's why many destroyers also, even though they have diesel engines, they have hybrid diesel drivetrain, even in Navy, because they know this. Lasers, coil guns, this boom boom guns. China claims that they have built a naval gun that is coil gun that has a serious oomph. And I do believe them. Coil guns are much easier to build compared to this. So trust me, you need serial hybrid. So this was my presentation on how you can have conversions and still increase your efficiency. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.